Well, good afternoon and welcome to our California Academy of Sciences live streamed tour of the universe. For the past couple of years, we've simulcast this program from Morrison Planetarium, but today we're actually piloting from the studio. And that means that I'll be able to respond to questions if you put them in chat and try to take you to some places that are of interest. In the meantime, my name's Ryan Wyatt. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences. And I'll be your pilot and guide for our tour of the universe. We're starting at a human scale. It's a good place to start since the universe is pretty big and we're going to be traveling much farther than even light could travel in the 25 minutes or so that this program will last. So even though the fastest thing in the universe could only make it out to not even quite to Saturn in that amount of time, we're going to take you out to the cosmic microwave background. To do that, we're using the OpenSpace software. It's free software supported by NASA, and you can download this same data yourself and play with it on your home computer. And what I'll do today is start at the International Space Station before heading much, much farther into space. The International Space Station is a good place to start because it is a human scale in that the distance across from sort of one side of those solar panels to the other is about the size of a football field. That's whether you're talking about a European football field or an American football field, is about the same size, about 100 yards, give or take, 100 meters. And inside some of these little capsules, you can imagine astronauts, including astronauts who might be spending a little bit more time there than they initially planned, are doing their work. So the ISS, as we call it, short for the International Space Station, is as far as humans travel out into space these days. There are, of course, plans to go farther out into the universe. Some people talk of Mars, but NASA is talking about the moon as a first stop. And we're waiting to see how that process goes. But in the meantime, this is kind of the limit. It's a few hundred kilometers above Earth's surface. And I'll tend to use kilometers instead of miles. Interchangeable kilometers are a little bit shorter. And as I pull away from the ISS, it might look like it's sort of plummeting into the ground. That's not the case. In fact, what's happening is that as we pull away, we're seeing the ISS recede into the distance. And we're actually over Asia right now. I'll go ahead and bring up the orbit line or the trajectory of the ISS so that you can see how it's encircling the Earth every 90 minutes. As we pull farther away, we'll be able to get a perspective on our own blue marble. This is our home planet Earth. As you can see, the ISS is just about crossing over China. And this is pretty much where ISS is right now. We update the data in OpenSpace to allow us to present accurate locations for everything in the universe, including things that are moving like the ISS. But as we pull away from Earth, we'll bring up a few other orbit lines, including, first of all, sorry, we're going to show those first, including the orbit of Earth's moon around our home planet. So we haven't gone very far from Earth yet. And as we pull far enough away, those lines on the right-hand side are kind of off in the distance. Those are the orbits of the planets around the sun. This line that encircles Earth is the moon's orbit. And if you can imagine, the moon is about 240,000 miles away, or sorry, 240,000 miles away, or about 400,000 kilometers. And that's, if you imagine you could drive a car for the lifetime of a car, you might drive it about that far, really crank up the odometer a bit. But astronauts traverse that distance in about a little over 3 days on the occasion when Americans traveled to the moon back in the late 60s and early 70s. And for purposes of this tour of the universe, what we'd like to note is that light, the fastest thing in the universe, which travels at about 186,000 miles per second, or about 300,000 kilometers per second, takes about a second and a half, give or take, to travel from Earth to the moon. That means when you look up at the full moon in the night sky, you're seeing it as it was a second and a half ago. And if you think about that, that's kind of like a brief pause in conversation, a second and a half. If we pull farther away, we'll begin to see the orbits of the other planets. You can see the stars in the distance, and eventually we'll traverse the distances between stars. But first, I'd like to introduce you to the scale of our solar system. We can see 4 orbits in here. Closest to the sun, Mercury, next out, Venus, then Earth, the third rock from the sun, and then Mars. Off in the distance on the left, you can begin to see some of the orbits of the outer planets. These 4 inner planets, the terrestrial planets, are Earth-like planets, are rocky worlds, and we've landed spacecraft on Venus and Mars. They're places that are quite different from Earth, but similar insofar as you can imagine walking on their surface. These terrestrial planets are huddled close to the sun. Earth, the distance from Earth to the sun is about 8.5 light minutes. So light takes about 8.5 minutes to travel from the sun to Earth. And if you think of that, that's maybe a quick lunch if you really ate a speedy sandwich or something. You might only take about 8.5 minutes. And as we travel around the solar system, you can see that the orbits of the planets are very much confined to the same plane. It's as if they're drawn on the same sheet of paper. Because of the way the solar system formed from a cloud of gas that was rotating billions of years ago, that flattened into a disk, and all of the orbits of the planets lie in roughly the same plane. So now if we pull far enough away from our solar system, you'll begin to see first the orbit of Jupiter entering the frame, then Saturn, Uranus, and finally Neptune. These are the 8 planets in our solar system. The 4 outer planets are dramatically different from the inner ones. The terrestrial planets, those 4 planets I mentioned earlier, are rocky worlds. The outer planets are much more gaseous, sometimes called gas giants. Sometimes Uranus and Neptune are called ice giants. They're much less dense than the terrestrial planets, but much bigger. We've explored those planets using spacecraft, and I'll mention a few of those in a moment. But before we get too far, I just want to point out one more measurement, and that is the distance across the solar system. So the distance across the solar system from one side of Neptune's orbit to the other, it kind of fades out here so you can't see, is about 8 light hours. So a second and a half, pause in conversation, 8.5 minutes, quick lunch, 8 hours. It's a good night's sleep. And then the distance to the nearest star is about 4 light years, which is a high school or college education. So the difference between interplanetary scales, as measured by the distance across Neptune's orbit, and interstellar scales, as measured by the distance to the nearest star, is the difference between a good night's sleep or a high school versus a high school or college education. And we haven't sent spacecraft out to different stars, to other stars. We've explored our solar system, but there are 5 spacecraft that will eventually escape the gravitational pull of the sun. They're traveling fast enough to do so. And we can use these as a sort of representation of how far we've explored into the universe using our sort of nuts and bolts mechanical devices. The 5 objects I've shown trajectories for here are the Pioneers 10 and 11 missions. Those were launched in the early 70s. Voyagers 1 and 2, those were launched in the late 70s. And finally, the New Horizons spacecraft, which is this one here, which was launched in the early aughts to visit the dwarf planet Pluto. So these trajectories are mapped out to the distances that each of these objects has traveled. And you can tell, if I pull just a little bit farther out, that our most distant spacecraft, the 4 spacecraft I mentioned that were launched back in the 70s, that's the Pioneers 1 and 2. I'm sorry, Pioneers 10 and 11, and then the Voyagers 1 and 2. Those 4 spacecraft have left the sort of protective magnetic envelope that surrounds the sun. So we say that they've entered interstellar space, but none of them have traveled as far as light travels in a single day. You can tell that because if you look at, again, that diameter of Neptune's orbit, 8 light hours, you can see that the farthest any of these spacecraft have traveled is about the distance that light travels in a day. So when we talk about distances in the universe, we're talking about vast, vast distances. And as we continue our exploration, we've already traveled farther than light could have traveled in the time that I've been talking, because it would take light about a day to get out to where we are in this virtual model of the universe, again, using the OpenSpace software that we use in the planetarium. And yet, we've got a lot farther to go. So let me go ahead and keep pulling away from our model of the solar system, our 8 planets, and our 5 fastest spacecraft that we've ever launched into the universe. And what we're going to do is, as we pull away from the sun's location, you'll notice that the sun is now brighter than it was a moment ago. That's because we had artificially dimmed the sun so it didn't wash out all of the stars in the background. Now we're displaying the sun in the same way, consistent with the way we're displaying other stars. The star here in the upper left-hand corner, traversing through the top of the frame, is Sirius. That's the brightest star we see in our night sky. But of course, the sun is our star, much closer than Sirius. Sirius is about 8 light years away. Our sun, as I mentioned before, is more like 8 light minutes. So we're now drawing the sun consistent with the way the stars are shown in our 3-dimensional model of the local universe. But we've still not traveled very far. As we pull farther and farther away from the sun, though, you'll notice that familiar constellations, and we have the Big Dipper here, kind of on the right-hand side of the frame, familiar constellations will begin to warp, and we'll begin to see that some of the stars shift positions as we move farther and farther from home. And here we're kind of drifting through interstellar space, and you can get a sense of the distribution of stars as we look at their 3-dimensional locations in the universe nearby. Now, one of the most exciting announcements from the past several decades in astronomy, and certainly one of the things that astronomers are spending a lot of time studying, is the discovery of exoplanets, planets around other stars. So other stars that have solar systems, or at least a single planet or more, like the one that, like our own solar system where we started our program. So we now know of thousands of these stars with planets in orbit around them. And these little circles don't represent those orbits. Rather, they represent the locations of those various stars. Some of these stars may only have one planet observed around them, or should say there's only evidence for a single planet around them. Others, we know of more than one planet in orbit around them, but there are still thousands of stars around which we have discovered planets. And given how difficult that measurement is, to discover these tiny planets around their parent stars, it's kind of amazing how many we found. And statistically, we think that there are probably planets around virtually every star in the sky. And planets are, in fact, a common feature of stars, at least in our galaxy. So again, each one of these little circles represents the location of a star with a planet orbiting it, at least one planet orbiting it. Now, I've mentioned our spacecraft, the Voyagers 1 and 2, New Horizons, Pioneers 10 and 11. Those haven't traveled terribly far away from our own planet, but We have made our presence known in the universe through other means. We broadcast radio signals that are strong enough to escape our ionosphere, and television carrier waves, radar, and in the past, atomic explosions all create radio signatures that can escape Earth's outer atmosphere. And if we wanted to think about how far those signals have traveled, we can draw a sphere around our sun. Right now, we're inside that sphere. We have nicknamed this the radiosphere. It's a sphere about 85 light years in radius, about 170 light years across. And that distance is chosen because the first strong radio signals, like I said, television carrier waves, radar, and then a little bit later, atomic explosions, those events created radio signals that could escape Earth's ionosphere, and they've been traveling for about 85 years, because it was basically back in 1939 that the strongest the initial sort of strong signals were released from Earth. So this sphere represents the kind of outer limit of where our radio signals, which are a form of light, a form of electromagnetic radiation, have washed across the universe. Now, for comparison, note that, let me slow things down because I think we were getting a little rocky there in our transmission speed. Notice that many of the planets lie inside the sphere, but many of them don't. And if we think about an astronomer living on a planet around one of these stars, if they had a radio telescope and could point it at Earth, then the astronomers inside the sphere, if they had the right technology, if it were sensitive enough, and if it were pointed in the right direction, could detect potentially signals from Earth. But even if an intelligent alien on one of the planets around a star located outside the sphere, even if they pointed their telescope in the right direction, they wouldn't be able to detect our signals because the light hasn't had time to reach them. So this sphere represents sort of the outer limit of our sort of electromagnetic footprint in the universe around us. So I want you to keep that in mind as we continue to pull away from our sun, which is now just a sort of barely detectable point inside at the very center of that sphere. Let me go ahead and turn off the exoplanet markers. And now we're going to continue pulling away from our location in the Milky Way galaxy. And I didn't point out the Milky Way as it appears from Earth, but we'll soon see how it appears, or might appear, I should say, from the outside. We live inside a collection of hundreds of billions of stars. We don't know exactly what it looks like because, as I mentioned before, our spacecraft have only traveled as far as light travels in a single day, our most distant spacecraft. But here, and I apologize because we're going to see a little bit of kind of background. I want you to ignore the kind of red dots in the background, and I want you to pay attention to the sort of brighter blue and pale, warmish colored image in front of us. This is a sort of best guess at the appearance of our Milky Way galaxy, our collection of hundreds of billions of stars in which we reside. And if you can still make out our radiosphere here at the center of the image, that's humanity's sort of technological footprint in the solar system around us, just a few pixels on our screen. And the entire diameter of our Milky Way is about 100,000 light years. So we started out talking about the distance to the moon, a second and a half, a brief pause in conversation. Distance across the solar system, 8 light hours, a good night's sleep. Distance to the nearest star, 4 light years, a high school or college education. Now we're talking about 100,000 years. That's Our species hadn't even left Africa 100,000 years ago. So now these distances, even by the sort of manageable measurement of light years and light travel time, these distances are becoming incredibly hard to wrap our heads around. And it'll get harder because the little red blobs, mostly off to the right-hand side of the image that I mentioned you should ignore earlier, if you pay attention to those now, those are actually the locations of not other stars, but other galaxies. Every one of those little circles represents another galaxy. We just passed the Large and Small Magellanic Clouds. They're two satellite galaxies of our own Milky Way. They're not nearly as large as the Milky Way, and they're actually sort of orbiting our own Milky Way galaxy. The faint dots that are fading up now are other kind of dwarf galaxies near our own. But some of these points represent galaxies that are as massive or even more massive than our own Milky Way. Some of them may have as many as 1 trillion stars. And some of them are much smaller, but many of them are about the same size as our own Milky Way galaxy. This is what we like to refer to as intergalactic space, intergalactic between the galaxies. And what you can begin to see, and the color coding sort of indicates associations between the galaxies. We'll kind of leave it at that. But these individual points aren't just scattered randomly through the universe. Instead, they kind of clump and cluster together. And that's an important feature of the universe in which we live. And in fact, this large clump of galaxies here just below and to the right of our home Milky Way galaxy is the Virgo cluster of galaxies, a collection of about 1,000 galaxies, much more massive than our own local group of galaxies, which there's that sort of tiny clump of smaller galaxies that surrounded the Milky Way. And so this clumping and clustering of galaxies is in fact a feature of our universe, as I said. Actually, we had a question here about the Andromeda galaxy. Let me go ahead and take us back in just to pay a quick visit to Andromeda. I think I can manage that. I'm going to avoid trying to look it up in the computer software and take us there directly. Instead, I'm going to try to kind of manage that on my own. We'll see how well I can do. But if we head back in here to our own local group of galaxies, Andromeda is a galaxy a little bit, actually fairly similar in size to our Milky Way. And I'm going to see if I can spot it by eye. If I can't, maybe I will go ahead and do what I usually don't do, which is expose the interface here of the software. And I'll see if we have, in fact, our Andromeda galaxy where I can pinpoint it. Unfortunately, it doesn't look like I can. So the question was about Andromeda and whether it would eventually collide with our Milky Way galaxy. So I apologize, I'm not going to be able to show you Andromeda, but let me just go ahead and answer that question. Basically, the Andromeda is the other sort of big player in the very nearby universe. It is indeed moving toward the Milky Way galaxy. And so eventually our two galaxies will collide. But what that means is a little bit different from a sort of head-on collision between two cars or even colliding stars or colliding planets. When galaxies collide, the stars are far enough apart, like those light years that I mentioned in terms of the distance between the sun and our nearest neighbor, that the stars themselves don't collide. They don't smash into each other, but the gas and dust in the galaxies does interact. And that can actually trigger the formation of new generations of stars. So eventually, and depending on which calculations you believe, eventually Milky Way and Andromeda will collide in something like 3 billion years, or it might be 5 billion, but in several billion years, the Andromeda galaxy, which of course now I've found is this galaxy over here on the lower left. Oh no, that's back. Sorry, I'm distracted and talking too much to myself here. So sorry, that's the Large and Small Magellanic Clouds. The Andromeda galaxy is much farther away. Eventually, Andromeda and Milky Way will collide, and when they do, they will potentially form a large elliptical galaxy. But first, triggering a burst of star formation as the gas in the two galaxies sort of combines to trigger new generations of stars. So with that, let's go ahead and continue our flight away from our Milky Way. Again, each one of these dots representing a galaxy perhaps as large as our Milky Way galaxy, perhaps even bigger like Andromeda. You can see the clumps of galaxies, including the Virgo cluster and the just below and to the right of the Milky Way. We're now fading up a giant atlas of galaxies that is basically a catalog that was executed by essentially a single telescope, or two telescopes, observing the sky night after night and making measurements of the distances to these galaxies. Now, looking at our depiction of this data set from the Sloan Digital Sky Survey, you might think that the universe is shaped like a bow tie. That's not the case. It's just that above and to the right and off to the left, those kind of wedges where you don't see any galaxies, it's not that there are no galaxies there. It's just that we haven't mapped that part of the universe yet. And as we continue our mapping efforts, we'll try to fill in the blanks. But again, I want to call your attention to the clumping and clustering of galaxies, even far from home. And as we near the end of the program, we're now, in terms of light travel time, talking about distances of billions of light years. So light from these points of light that are just appearing on the edge of the screen will take billions of years to reach our Milky Way galaxy, or I should say took billions of years to reach the telescopes that made these observations. And the punchline to this is that looking out into space is looking back in time. So these points of light that are close to our camera here that are kind of flying in front of us, those are billions of light years away from our home and the Milky Way, orbiting the sun here on Earth. And we're observing them as they were billions of years in the past. And the punchline to this is the kind of mottled image that is appearing in the background here. That is the cosmic microwave background. It's a baby picture of the early universe. And unlike a photo of your grandparents, this is kind of like a heat map. The dark regions are regions that are a little bit cooler than the bright regions, which are a little bit hotter. And the difference, it's a very high contrast image, the difference between the hottest parts and the coolest part is a difference of 1 part in 100,000. So the dark regions are a little tiny bit cooler than the bright regions, and that corresponds to a similar difference in density. So the cool regions are a little bit denser, the hot regions are a little bit less dense. And what's amazing is that the action of gravity over billions of years, along with the presence of dark matter that we don't really have time to get into, pulls that structure together, that very tiny fluctuation in the mass density of the early universe, pulls that mass together to form the clumps and clusters of galaxies that we see close to home. So this baby picture dates back to a time when the universe was a few 100,000 years old, but the universe now is about 13.8 billion years old. So the universe was very young indeed. Very tiny fluctuations in the mass distribution of the early universe that form the clumps and clusters of galaxies that we see close to home. So this is the really big picture. Before I take us home, I just want to mention one thing. It looks like we are at the center of the universe. And that's true in the way that we're depicting this model of the universe. But remember, this is a 3D model of the universe that's compiled from astronomical observations. It appears that we are at the center of the universe simply because we're the ones drawing the picture. We're plotting the distances of these objects away from us. So we appear at the center of the universe in the here and the now, while the cosmic microwave background appears in the distance 13.8-ish billion years ago when the universe was much younger. And it's not that we're the center of the universe, it's just that we're the ones drawing the picture. So with that, let's go ahead and fly back home. I'll take you through the Sloan Digital Sky Survey. We'll travel slow enough that that our live stream doesn't choke on it. And you can see in the sort of bluish aqua colored points, the clusters of galaxies that were formed by the eventual action of gravity on those tiny fluctuations in the cosmic microwave background. As we fly back toward the center of our model of the universe, we're seeing the regions to the left and upper right where we haven't finished mapping the universe around us, and yet hundreds of thousands of galaxies we have mapped in these sort of butterfly-shaped or bow tie-shaped structures that are an artifact of us making the observation. Flying into a collection of about 30,000 galaxies, which is actually, instead of being the work of a single telescope, is the work of dozens or hundreds of astronomers working over a period of decades to map the locations of these nearby galaxies. And each one of these points represents a galaxy that might be as large as our Milky Way, with hundreds of billions of stars inside. As we approach our Milky Way, we'll see our dot replaced by the spiral structure of our Milky Way galaxy. These little points that are fading out are the locations of our companion galaxies in the local group of galaxies. We left that radiosphere up, so as we approach our Milky Way, we're seeing the sphere that represents our technological footprint in the universe around us. So actually, let me go ahead and fade that out. Oops, started spinning a little faster than I wanted here. Slow that down a bit. We'll go ahead and fade out our radiosphere and continue our dive back down toward our solar system. The reverse of what we saw when we left will happen. The sun is currently depicted the same way the other stars in our galaxy are, but now as we get closer, we'll fade down. The extra bright sun will see the trajectories of those 5 fastest nuts and bolts spacecraft that we've sent out into the universe around us, have traveled about as far as light travels in a single day. We'll go ahead and fade those out as we approach our own home planet Earth, the third rock from the sun, the important planet for those of us who live here, because it is our home in this vast universe, the one planet that we know of that supports life, and the opportunity to share our knowledge of the universe through a live stream program. I want to thank you for tuning in to our California Academy of Sciences tour of the universe. We do this the last Wednesday of every month at 4:30 p.m. Pacific. Thanks for joining us, and I hope you have a great afternoon.